When an engineered system suddenly gives way, it is rarely an act of mechanical bad luck. Metal, concrete, and code do not fail spontaneously. This schematic graph illustrates an operating envelope. Green borders represent strict limits, temperature, pressure, or volume, where a system functions safely. When external inputs force a system outside these tolerances, it does not adapt, it breaks down. The deadliest technological disasters in history are not mysteries. They share a single definable root cause: boundary condition violations. To understand how these cascading failures occur, we have to reverse engineer them. We will look at specific historical events to trace the exact thermodynamic, spatial, and data boundary violations that triggered them. Getting to the truth of a disaster means discarding the historical drama surrounding it. We have to look strictly at the raw physics of what happens when a machine is pushed too far. Thermodynamic boundaries dictate the precise thermal and power limits of a material. We see a stark violation of this on the morning of January 28, 1986, prior to the launch of the Space Shuttle Challenger. The environment at the Kennedy Space Center was unusually harsh, with ambient temperatures at the launch pad dropping below freezing. This cross-section schematic shows the joint of the solid rocket booster. The vital components here are the rubber O-rings, which act as seals to prevent pressurized hot gas from escaping the rocket. Like all materials, this rubber had a defined thermal operating limit. The freezing temperatures at the launch pad dropped the material well below that limit. The rubber became stiff and lost its elasticity. It was physically incapable of expanding to seal the gap, allowing superheated gas to burn right through the joint. That escaping thermal energy acted like a blowtorch, rupturing the external fuel tank and instantly destroying the shuttle 73 seconds into flight. We see a similar violation of limits, not of ambient temperature, but of reactor power output, during a safety test at the Chernobyl nuclear power plant later that same year. This dual-axis line chart tracks the reactor's condition leading up to the disaster. The procedure required the reactor to operate between 700 and 1,000 megawatts thermal. Instead, operator error dropped it to just 30 megawatts. At this extreme low, xenon gas built up rapidly, poisoning the reaction and making the core highly unstable. To compensate, operators removed most of the control rods. When they finally initiated an emergency shutdown, a fatal design flaw emerged. The rods had graphite tips. Inserting them created a positive reactivity feedback loop, driving the nuclear reaction further upward instead of stopping it. The sudden, uncontrollable surge in power instantly vaporized the coolant, triggering massive steam explosions that blew the biological shield off the core and released radioactive material directly into the atmosphere. The facility was obliterated. The architecture simply could not contain the extreme energy spike. Whether the system is a multi-stage rocket or a nuclear containment core, the outcome is the same. When pushed outside their thermal and power parameters, aerospace and nuclear architectures disintegrate. Spatial and volumetric boundaries are just as unforgiving. The RMS Titanic was hailed as an engineering marvel, but in reality, it was an incomplete containment system. Looking at this lateral cross-section of the hull, we can see the vessel's watertight compartments. Notice the specific geometric limitation. Many of these steel bulkheads only extend upward as far as E-deck, several levels below the main deck. The ship was calculated to stay afloat with 4 compartments flooded. Striking the iceberg flooded 6. This added mass altered the vessel's center of gravity, pitching the bow downward and lowering the height of the bulkheads relative to the waterline. The ocean simply spilled over the top of the walls from one compartment to the next. This spatial failure was compounded by a capacity failure. Due to outdated regulatory parameters based on vessel tonnage rather than human occupancy, the ship carried lifeboats for roughly 1,178 people, while over 2,200 were on board. A similar violation of physical capacity occurred in civil engineering at the Banqiao Dam in China's Henan province. The dam was constructed with a specific hydrological baseline. Its operating envelope was designed to handle 500 millimeters of rainfall over a 3-day period. This split chart contrasts the dam's maximum spillway discharge rate against the actual water volume it received in August 1975. Typhoon Nina stalled over the watershed, dumping over 1,000 millimeters of rain in just 24 hours, shattering the 500-millimeter boundary. Operators desperately needed to open the floodgates wider, but the storm had knocked out communication lines, isolating the dam from higher authorities. Without manual intervention, the spillways could not discharge water fast enough. The excess water volume crusted the structure, resulting in a catastrophic collapse. A wall of water several meters high wiped out entire villages downstream, triggering a chain reaction that destroyed more than 60 other dams. Containment systems do not quietly fail. When physical volume exceeds hard-coded geometric limits, they become active mechanisms for sequential flooding. Modern architecture relies on multiple systems working together, meaning the boundaries aren't always physical walls. In 1999, NASA lost the $125 million Mars Climate Orbiter due to friction at a data interface. This diagram outlines the data streams feeding into the spacecraft's navigation module. The interfaces were mismatched at the fundamental level. The contractor, Lockheed Martin, programmed their software using imperial pound force seconds. The NASA team expected the output in metric Newton seconds. Because this unit discrepancy went uncorrected, it created a compounding multiplier of 4.45 over the spacecraft's 9-month transit. Instead of entering orbit at a safe 87 miles, the data drift pushed the orbiter down to roughly 35 miles, where atmospheric drag tore it apart. Software interfaces manage data, but physical interfaces manage isolation. At the Union Carbide pesticide plant in Bhopal, India, a failure at a physical boundary caused one of the deadliest industrial events in history. Looking at this pipe schematic for storage tank E610, we can see where the system's boundary broke down. During routine maintenance on connected pipes, water bypassed isolation valves that were either malfunctioning or improperly secured, pouring directly into 42 tons of highly toxic methyl isocyanate. The mixture triggered a massive exothermic reaction. The rising temperature and pressure rapidly exceeded the containment parameters of the tank. Just after midnight, the primary relief valve burst wide open. A deadly cloud of toxic gas was vented directly into the air, drifting over sleeping residential areas and resulting in thousands of fatalities. A complex system cannot protect itself if its individual components are misaligned. It is only as secure as the data or physical interfaces connecting it together. This 4-quadrant split screen illustrates the failures across these events. Whether it is aerospace hardware, nuclear physics, software engineering, or maritime design, they share the exact same structural mechanic. A critical parameter breached its operating envelope. Despite vast differences in application, hardware remains inherently tied to the mathematical boundaries placed upon it. In engineering, bad design and human error are functionally the same thing. Both represent a failure to recognize, enforce, and verify boundary conditions. External demands, like the political pressure to launch a shuttle on schedule, or the electrical grid's demand for a reactor test, cannot negotiate with thermodynamic limits or spatial reality. The physics will always win. Preventing these cascades requires rigorous systems engineering. It means aggressively validating assumptions at every single interface and actively testing the constraints. Mathematics govern the edge of what a machine can survive. Respecting that limit is the only way to prevent complex systems from engineering their own destruction.